I'd really like to welcome our very first speaker, James Field, who's CEO of LabGenius. And as you'll see, LabGenius is developing some amazing technology to move forward drug development. With that, James.
Thanks so much, Nathan. Morning, everyone. When I looked at the amazing set of speakers that Nathan had put together, I was like, why have you asked me to be here? And then that was only further compounded when I saw the list of delegates. So I feel like I'm just a little bit of light entertainment to ease you into the real thing, and I hope I don't disappoint, at least on that front. So I'm the CEO and founder of LabGenius. We're a venture-backed synthetic biology company based here in London, and we're on a mission to autonomize the discovery of therapeutic proteins. I set out on this journey personally a few years back, and you know, when I first decided this is what we were going to do, I just went home and I said to my parents, "We're on this mission to autonomize the discovery of therapeutic proteins," and they were like, "Proteins?" And you know, this is a reaction that a lot of people have. People are used to the proteins that they ingest inside the body, so this is a great product, pure protein. If you drink it, you get 35 grams of really good protein. But the cool thing is what happens after you've drunk it. So you swallow it, it goes into your stomach, the low pH sort of starts to break it up, and then you have all of these digestive enzymes in your GI tract that chop them up into small pieces. They get ingested into your body, and then suddenly something really nice happens, which is they get made into all of these really cool molecules. So these are proteins as biologists see them. These are the nanoscale actuators of life, and the 3 billion base pairs of DNA in your genome encodes approximately 20,000 of these different molecules. And these are the reasons that we're healthy, and when they go wrong, they're the reasons that we get sick. And so there's a huge opportunity here if you can start to really play with the fabric of life and engineer molecules, protein-based molecules, to do awesome things. And you know, this is something we've been doing for the last 40 years. So as a class of molecules, they have this incredible potential to alleviate a ton of suffering, so make people live longer, healthier lives. And if you're putting a sort of financial cap on, they also make big bucks too. And this is just a few of the numbers from the top-selling protein molecules. All these are therapeutic agents. And the things that you'll sort of take home from this is that they can be used to treat a ton of different diseases. They make a ton of money, but if you look at the number of proteins that are on the market, you have a very very small total number of molecules, and these are the ones that are making the big bucks. And this is the thing that I guess I find really upsetting, which is here's a class of molecule that have the potential to do so much for humanity, but over the last 40 years of trying to engineer and make these molecules, as a species, we've only managed to get 240 of those to market. And so both the shame but also the huge opportunity is addressing that delta between what we've achieved to date and what we could potentially achieve in the future. And this is probably, for me, one of the most exciting opportunities that exist. So applying different sets of technologies to address that delta, that untapped potential. So it's worth starting off just by thinking, why is actually engineering these molecules so difficult? There are lots of pharma companies who have incredibly smart people working on these problems, and yet, even with all that resources, it's still really difficult to get these molecules to market. And it's because it's a really tough problem. You're not just trying to engineer these molecules to do one thing, but you're trying to engineer this absolute ton of different biochemical, biophysical properties, as well as sort of commercial considerations into these molecules simultaneously. And you can have a molecule that looks really great, but 12 years down the line from when you started that project, it turns out that that's a little bit too toxic and it's not going to get to market. So it's this really challenging multi-factor optimization problem. And we see that problem as a search problem. And that seems like you're all like, oh yeah, that makes sense. We're at Google. This is a search problem. That's why Nathan's got James here. But a lot of biologists don't see it as a search problem. And this is sort of a new lens, a new way of looking at this challenging area. And I'm going to explain to you why it is a search problem. So you can take any protein that exists and you can represent it as a linear chain of amino acids. So it's like beads on a string. There are 20 different amino acids, and so you can represent that molecule in this sort of format. And when you suddenly look at this molecule or any protein molecule in this format, you're like, okay, I get this now. Different positions, different amino acids at each of the positions, and really this is just about flipping ones and zeros. This could be a search problem. And the really exciting thing is DNA, so DNA is the molecule that encodes these proteins, it's super cheap to synthesize. So if you could look at this and you knew where to put the ones and where to put the zeros, you could synthesize a piece of DNA in a few hours, have it shipped to you, start making that protein really easily, and then you're printing cash. It's not that simple, but it's like the challenging bit is not making that molecule if you get the right sequence. The challenge is finding that right sequence. And so it turns out that it's this really difficult search problem. And the reason it's so difficult is because you're trying to simultaneously optimize for all of those different properties. And actually, if we imagine this as a solution space, so this is sort of a very sort of illustrative purposes only, but if you imagine all the different protein sequences that could exist for a given problem, and your objective function is to find the molecule that has that right blend of biochemical, biophysical properties, you end up with this landscape that's incredibly difficult to traverse. And this is where you can start to apply technology to make it more easy to navigate and traverse. But the thing about sequence space is, although it sounds like this very foreign concept, it's something that we're actually all instinctively born with. We are actually expert systems who both understand the topology of this landscape and in some circumstances know how to navigate it. And I'm going to digress really quickly because I think it's quite an interesting point. So if we imagine all of the different species on Earth, and we imagine this sort of sequence space at the organismal level, describing where those species sit, it's a little bit like habitable planets adrift in the universe in the sense that those islands of genetic viability are few and far between. And we actively, intrinsically, instinctively already know this. So this is a painting called The Flirtation. And if you're an alien looking at this, you would be like, OK, there's one member of this species flirting with like another member of this species. Why has he chosen to flirt with a member of the same species rather than, say, the apple or the tree or anything like that? And really, it's funny because it's so instinctive. But actually, from this objective view, actually this human sexual attraction really is just this inbuilt algorithm of how you traverse this very spiky sequence space. But so we can do that pretty well. But back down at the protein level, unfortunately, I at least wasn't born with the instincts to know how to traverse that. So how do you start to navigate it? Well, if we think about solution spaces in general, there are three basic ways to start navigating them. There's virtual search. So if you live in the matrix, then the world itself can be compressed or described computationally, and you can simulate it. And that's really incredible. If you can accurately capture the dynamics of a system computationally, you can very rapidly start to explore where are the high-performing areas. And there's some amazing work that's been done on the engineering side of where you're doing multi-factor optimization for systems that you can fairly accurately represent computationally, and you get these amazing designs coming out of it. But biology is really complex. It's impossible to really accurately capture biology on a computer from first principles, principally because we don't fundamentally understand exactly how that system works. So how do you start to grapple with this biological complexity? Well, the good news is that problem's already been solved. And I can prove it's been solved because we're all sitting here. So we are the product of this process of Darwinian evolution, which, when you think about it, is a process that autonomously generates both new knowledge and new technology in a way that's completely non-human, which is really exciting. So this process of diversification and replication and selection, really you can think of as just this algorithm that is searching through the solution space, looking for high-performing solutions to specific problems. So here's a great example where at the top you have a dog, and the one below is a thylacine. So this is now extinct, unfortunately, but it's a marsupial, so actually completely unrelated to the dog. But here you can see Darwinian evolution has searched through this landscape to find a convergent solution for a same set of problems, for the same ecological niche. Problem with Darwinian evolution is it's super slow, and I'm really impatient. So you can't rely on it to solve the problems fast enough. So this is where we can start to think around using technology. And there's this process called empirical computation that we apply specifically to this problem. So to think about empirical computation, it's worth very briefly thinking about the standard scientific discovery process. And so this is Rick. He's a really accomplished scientist, and he works in this cutting-edge facility in his daughter's garage. And you'll see that he's quite old, and over the course of his life, he's accumulated a lot of knowledge. And that knowledge enables him to invent, to come up with new designs that he conceptually produces from his understanding of the world. And then he fabricates them with his hands, he tests whether it works, and he iterates around this loop. And anyone who's sort of done a PhD in, say, biology or something, it's this kind of very painful process of, I have an idea, test the idea, it doesn't work, try again. This is what it kind of feels like, right? So I don't know if you've seen this video. This is one of my favorite videos. So this is a monkey who's about to see a magic trick.
Okay.
So the reason that this is like one of my favorite videos, because first you laugh and you're laughing because the monkey has this world model in its head that it's formed through its own experience. And then it experiences this thing or this feeling of surprise when it realizes, oh my God, my world model is not correct. And when you're a biologist trying to engineer biology, like this is what it feels like on a daily basis, because you can't grapple with the complexity of life in this thing. So it's very difficult to apply the traditional scientific process of discovery to engineering biology. So this is empirical computation, which is very much like the traditional scientific discovery process. But instead of using your brain, you're trying to get past this cognitive barrier by deploying ML, in silico compute and storage. And you're trying to get past this process of manipulating things with your hand by using robotic automation and analytics. And so when you deploy this approach in a closed-loop system, you can start to interrogate properties in the real world that are too difficult or complex to purely simulate. So I'm just going to go through how these empirical computation engines work. So at a very simplistic level, you have the world of bits and the world of atoms. And in the world of bits, you generate your hypotheses, and in the world of atoms, you test them. And all empirical computation engines have 4 basic technologies or parts. So a bit handler, something to handle your bits. How do you get your hypotheses into the real world? These are your bit-to-atom converters, your atom handlers for actually doing your experimental testing, and then your atom-to-bit converters to go back into the world of bits. Really simple, but this architecture can be deployed to pretty much any scientific problem. For the one that we're tackling, this is what it looks like. So we generate a lot of hypotheses computationally, because we're engineering proteins. What this effectively means is trillions of different DNA sequences that we think will encode high-performing proteins. We then use DNA synthesis to manifest them, to translate them from the world of bits to the world of atoms, robots to test them, and then next-generation sequencing, which is this really cool technology which takes DNA sequences and reads them back into the world of bits. And then you iterate round and round that loop in your search process as you search through that space. Now, I think it's sort of it's a requirement for anyone who's building one of these engines to create some kind of video to show off the cool robotic automation piece. So I asked an intern to do this for me yesterday, and she's come up with this really, really, which I like, inspiring video, at least from my perspective. So this is what a little bit of the stack looks like in our offices in Bermondsey. And you know, this is very much sort of just scratching the surface of what we're looking to build. But when you're a biologist and you spend your PhD in the lab with that pipette, this is just pure delight. So building these engines is really tough. And the reason that building this engine is really tough is the whole company is based on this thesis that engineering proteins is too complex to fit in your skull, in a single human skull. And it's even too complex to fit into a team of people's skulls. So the way that you start grappling with the complexity is that you build the engine that no single human can create, but a group of humans can. And so I'm really fortunate to work with 30 incredibly talented scientists and engineers who span automotive engineering, now robotics, systems engineering, synthetic biology, microbiology, data engineering, data science. It was all that sort of multidisciplinary mashed together to build this engine. Yeah, so this is when we started out on this journey. This idea that you could take protein sequences and you can predict their function. A lot of people said it's just not going to work. And so this is a picture. This is called the background of this is doubting Thomas or Didymus. So the background to this is, as everybody knows, it's in the Bible, so it's factually correct, that Jesus died and was then resurrected. And there was this guy called Didymus who was just like, this doesn't quite sound right. And John the Apostle was like, no, this is legit. It really happened. Didymus was like, I just don't believe it. And then Jesus turned up and said, no, it is true. I am back. Pop your finger inside. And then Didymus was like, OK, I'm with you now. So I felt like when we were building the company, it was this same thing. So I was saying like, right, this is what we're going to do. We're going to sequence a lot of DNA, and we're going to work out how these sequences encode function. And everyone was like, you've got to model the structures, dude. It's not going to work unless you model the structures. And so this is like the big thing for us. Can you go directly from the DNA sequence to the fitness of that protein without even touching function? Yeah, when we started on this journey, this was like the big question. And collectively, I think we've sort of reached a consensus now that it is possible. And so here's some work that was principally done by Katya, who's actually here in the audience, along with AL on our data science team. And I'm just going to talk you really quickly through how it works. So if you're a biologist, you love jellyfish, and you love jellyfish because they glow green. They produce this molecule called green fluorescent protein that's really nice and easy to work with and allows you to prove stuff. So this is what the structure of that molecule looks like, and this protein is encoded by the sequence of amino acids, which is represented by this linear chain of letters. And the challenge here was, could you sort of start mutating this sequence, so create sort of many different permutations of it, and then using computational methods predict, without knowing what the structure looks like, whether these molecules will actually work? And it turns out that you can. And the way the team proved this was to take this data set, so this data set of all these different sequences, each of which encoded a different fitness. So some of those molecules were broken. They didn't fold up correctly. Or maybe they did fold up correctly, but they just didn't work. And those that did. And they took 15% of that data. And using machine learning, they were able to build a model around that so that they could then take new sequences that the model had never seen before and predict whether they could work or not. And this was super exciting. But it's not just enough to be able to model sequence to fitness. You have to know how you can start searching that space. And so this is like the next part of the process. So the objective here is not to take the entirety of biological complexity and model it and be able to just do everything like in the matrix. Probably impossible. The intention here is to be able to capture a piece of like a portion of that puzzle and just extract enough insight so you know where to intelligently take your next step. How do you intelligently search through that almost infinite space? And so this is the search strategy. You have this very, very complex fitness landscape. You then try and deconvolute based on the different features, the different biochemical, biophysical properties that you're interested in, build models around those, and then optimize across those models. So this is what this process sort of looks like, and here's some amazing work done by Eyal, who's also here today, and just talk you through what this looks like. So every time we go from the world of bits into the world of atoms, we're not just taking single hypotheses, single designs across. We're taking trillions of them across at a time. And we need to make sure that the trillion that we're taking across are the best possible trillion that we can predict. Because even though you're testing a trillion things physically here in the real world, that's an infinitesimally small percentage of the total space that's available to explore. And most of it won't work. So as we have these models, and so you have effectively a starting library, a starting set of designs that you want to take across. And that's represented here on the far left. And then you have the sort of the mapping. How does that set of designs map onto the biological space? And that's this middle panel where you have the sets of A, C's, T's, and G's, which are the DNA base pairs. and on the y-axis, the different positions in a protein. And what you'll see here when I click play is you'll have this in silico interrogation of the model in order to redesign the libraries in an iterative process. So this is like in silico evolution, so that you can optimize for whatever your biochemical, biophysical properties are, your new library design, such that when you take it into the real world, you're testing your best trillion things. And so what you're seeing here, and I think in all my experience in science, is pretty much the same things. When things start moving up and to the right, it's a good thing. And so as a CEO, that's like my takeaway from the hard work of the data scientists. But they're here in real life, and you can get the really nuanced understanding from them after. So how are we deploying this technology? Obviously, we can't boil the ocean. We've got to be pretty focused. And this is where there's some symmetry, I think, in this talk. So as I said at the beginning, you drink that really cool thing of pure protein, and it goes into your GI tract, and it gets broken down into a ton of little pieces that then get reabsorbed into your body. The problem with that, the problem with the fact that your body has evolved through Darwinian evolution to break down all of those molecules means that you can't deliver any protein therapeutics orally. And so this is a really challenging problem that we're trying to address as one of our programs. So the challenge here is, can you re-engineer therapeutic molecules? Can you search through that solution space to find variants that both have all the biochemical, biophysical properties required to have their therapeutic effect, but can also resist degradation? And so we're working with an amazing company called Tillot's, located in Switzerland, in order to develop orally available therapies for inflammatory bowel disease as one of our first programs. But the platform itself is obviously can be tailored to address a whole suite of different challenges. So I just wanted to conclude by saying we're fortunate to be based here in London, down at the biscuit factory. So this is an old biscuit factory where they no longer make biscuits, but they did previously. They invented bourbon biscuits there. We'd love to host anyone who's interested in seeing our stack in real life and meeting the team. So just wanted to thank you all for your attention, and yeah, great to be here.